So let's say a few things about antennas and the idea of millimeter wave. If we're in this sort of mid-band, this 3 gigahertz, the wavelength is about 100 millimeters, and therefore the receive antenna could be configured such it is the same wavelength. And that's fine. You've got quite a large collecting area there. So you've got a big bit of copper hanging out there in the air, which is grabbing the electromagnetic signal as it passes by. So you've got a radiation from the mobile, of course, and you've got a large surface area here with which to grab that electromagnetic signal. Now, of course, we all know that as you increase the frequency, the path loss increases. But if you look at the formulas, if you look at something like a derivation of the free space path loss model, then what you find out is that it's not necessarily the frequency, it's more to do with the size of the receive antenna, because every antenna has what's referred to as an antenna aperture, and that antenna aperture is defined through the wavelength of the electromagnetic spectrum. So if we define the size of the antenna based on the wavelength, then what we have is at 30 gigahertz now. Well, we're an order of magnitude less now, so the size of the wavelength is about 10 millimeters. And if we design the antenna around about that 10 millimeter wavelength, then we've actually only got 1% of the area in which we can collect the energy, when compared to the previous example. So this mobile is still transmitting, there's still a sort of radiating wave here. But of course, as you can see, the amount of area over which I'm able to collect that signal, it's massively reduced. So that leads to this tendency or this knowledge that propagation loss increases with the frequency. But we can reverse that situation a little bit. If the reason we're collecting so little energy is because the antenna is so small, well then why don't we just make the antenna big again? So at the millimeter wave, we've increased the number of antenna elements. We're back to approximately where we were in terms of collecting the energy. So we're able to collect a lot more energy, and so the propagation loss now is maybe not entirely, but it's more independent of the frequency. So effectively we have a much, much higher gain antenna here, and the collecting area has also increased by a considerable amount. Now we could just leave it at that. We could say, right, let's put all these little patches up there, collect as much energy as we can, and just feed it back to like a normal receive process. But to be honest, if we're going to go to the effort of building an array of elements like this, we might as well exploit the fact that we've got lots of different elements in there and start thinking about MIMO, thinking about beamforming, and thinking about some of those other techniques that can massively improve the overall efficiency of the radio cell, of the system in general. And also to try and improve the signal to noise ratio for the users out in the radio cell. So both in the uplink and in the downlink direction, anything we can do to improve the signal to noise ratio is a massive improvement in the overall efficiency and potentially even the bit rate that can be experienced by the users. In the millimeter wave bands, because of the size of the antenna, it seems like it would be more practical to use these arrays at those millimeter wave bands, but this is not without issue. And it doesn't necessarily mean that we can't use antenna arrays of this style in the lower frequency bands. If we are constrained in terms of space, so the actual physical size of the overall antenna, it just means we won't be able to have as many antenna elements, so maybe not as many beams or not as many layers on the radio interface as we would otherwise like. We can still exploit that advanced antenna technique in any of the bands.